Hi everybody, this is Ryan, and today we're going to talk a little bit about set theory and logic. So let's talk about set theory a little bit. So when we deal with sets, a set is a collection of distinct objects called elements. So you need to understand what a set is, and you need to understand what an element is. So an example of a set is something like this. 1, 2, 3, 4. That's a set of 4 numbers, and each number is an element. So this is a set. That's a set. And these in here, that is an element. Set notation uses symbols to create statements regarding the set. For example, the symbol E represents the phrase is an element of. So here's a symbol. And then it's represented is an element of. So we would say that 1 is an element of this set. There's that symbol. The empty set is a 0 with a line through it, is a set with no elements. A subset is that little c, is a set that contains another set. And a proper set is a set that contains another set but is not identical. So we can also do set operations. How can we interact? How sets interact with each other? So this one is a union. And the key word there in a union is the word or. They're in one set or another. The next one is an intersection. And an intersection is a set contains only what is in both sets. So we would usually typically have an and on that one. We have a complement. So a complement is either this little tilde symbol or a little c. That's complement. So that means in one set, not the other, or it's what's not in it's what's not in the set. And difference is everything present in one set but not in the other. Okay, so let's take a look at this example. So the first thing we need to do is we need to identify the universal set. Since no universal set is given, we assume it consists of all natural numbers relevant to the given sets. So you'll notice here we want a complement, and this is an intersect, which means and. It's a set that contains only what is in both sets. And then we got set A. So the first is to find the complement of set B. The complement of B includes all elements not in B. Assuming the universal set is at least all numbers in A, we focus on numbers in A that are not in B. So A we know is this one. B we know this is A. And we know this is B. The elements in A but not in B are the following. So we want to look at in A but not in B are these 6, 8, 10, and 12. So what we would do is we would want to do the A intersect a complement of BC. And that would just be the elements. So we wanted to connect between the elements in A and this set. So this set, in this set, and this set. Both of those. So which elements are in both of those sets? These numbers here are in that set, and they're also in this set. So this would be the set 6, 8, 10, and 12. You can visualize that through a Venn diagram. So A contains 2, 4, 6, 8, 10, 12. B contains 1, 2, 3, and 4. You'll see that both sets contain 2 and 4. But we want the elements in A intersect the elements not in B. So that would just be these 4 numbers right here. So when you think about a Venn diagram, the intersect happens where they intersect right there. That is the intersect, or the overlap. That means the elements are in both sets. And so if we think about another example here, let's look at a very simple one. Let's do 1, 2, 3. That's set A. Let's do set B. And let's call that 3, 4, and 5. If I was to make a Venn diagram of these two sets, this is set A over here. This is set B. So in set A, I would put 1 and 2. Set B, I would put 4 and 5. And in the intersect, I put 3 because 3 is in both sets. So A intersect B would be 3. A union B would be the elements in both sets would be the set 1, 2, 3, 4, and 5. So that's a simple example of kind of how all this works. So let's talk about a little bit of logic. So Boolean logic. Boolean logic combines multiple statements that are either true or false into an expression that is either true or false. Two statements joined by the word and is considered an intersection, which we talked about that. So and it goes with intersection. And both statements must be true in order for the entire expression to be true. Two statements joined by the word or considered a union. And either statement can be true or both statements can be true. So some qualifiers. A universal qualifier translates to for all or for every and uses the symbol A. Existential qualifier transitions to there exists and the symbol backwards E. Negativing a qualifier statement creates the opposite set to be created, which can often be more concise. When we negate a qualified statement with a universal qualifier, we get a statement with existential qualifier and vice versa. Now, we remember these things. We've been through this a couple times. We talked about this already. This is the union, this is the intersect, and this is the complement. Now, when we deal with Boolean language, we go from we go from an upside down U to an upside down V. Let's make that a little bit better. We go from an upside down U to an upside down V in Boolean. And we go from a right side up U to a right side up V in Boolean algebra. So we're going to create a truth table. So logical conditional statements stating that a statement P ascendant implies that Q is a consequence. Implications are typically written as P implies Q and is translated to if P then Q. So here is a truth table. If both are true, they're true. If the first one is true, the second one is false, it's false. If the first statement is false, the second one is true, it's true. If they're both false, the consequence is true. So let's talk about equivalence in De Morgan's law. How do we break down negation statements to prove equivalence? A conditional statement and its contrapositive are logically equivalent. The converse and the inverse of a statement are logically equivalent. So that's this stuff here. Okay, so types of arguments. There's inductive arguments, use examples to draw conclusions. Deductive arguments use general statements to draw conclusions. An inductive argument is never able to prove the conclusion true, but it can provide either weak or strong evidence to suggest it may be true. So for example would be, if it is cloudy, then it might rain. Okay. Valid deductive arguments assume premises are true. Sound deduction argument is valid and premises are known to be true. So that would be an example of 1 plus 1 is 2. So here are some fallacies. There are 9 types of logical fallacies to be familiar with. So these are the 9. Take a look at those. Here are some definitions of each one of them. Take a look at those. And now let's use that information to identify some fallacies. So let's take a look at the first fallacy. You can't be serious about climate change. You drive a gas guzzling car. So which of these, which fallacy would that be? I think it would be ad hominem. Because you're attacking the person instead of addressing their argument. About the next one. If you use our fitness app, you will become a professional athlete. In this one, I'm kind of torn. I think it's either going to be post hoc, meaning assuming that because B comes after A causes B. I think that could be one thing. Another possibility, I think, we could do correlation implies causation, maybe. I think either one of those would probably be a valid answer that you could defend. How about the last one? Either you're with us or you're against us. In my mind, that one would probably be false dilemma. That's presenting two options as the only options. So I think that would probably be false dilemma. So I hope you enjoyed this video. If you have questions, please let me know.